Okay, now we have related rates example dealing with a cone. And remember, a cone is a three-dimensional shape. It has a radius at the top of the circle at the top. It has a height. It also has this length right here. That's the slant length, but for most of these, we're going to need to relate the height and the radius together. But this is three-dimensional, so this is going to be a volume problem. Let's go. Okay, so a conical paper cup is 30 centimeters tall with a radius of 10 centimeters. The cup is being filled with water so that the water level rises. Okay, so the height is what is rising. So the dH dt is rising. At what rate is water being poured into the cup? Well, if water is going into the cup, that would be the volume. So we're looking for volume. So we state what we know. We know that the rate of water rising, or height, dH dt, is rising at 4 centimeters per second. The diagram, I'm not an artist, so please don't mock me. That radius is 10 centimeters. The height of the cone is 30 centimeters. The formulas, well, this is interesting. So this is the formula for volume, and this is the volume, the formula for surface area. But if you notice, the radius and the height, we can go ahead and relate the radius and the height without using the surface area. It's always easiest if we don't use two different formulas. So what we have to do is say that, well, 3 times the radius, 3 times 10 is the height. So if we want to get the radius by itself, we just divide both sides by 3. And the reason we want to get the radius by itself is because we want to put the radius in terms of h, since what we're given is the change in the height. So radius is the same as height divided by 3. And what we need to find is how fast is the volume changing at the exact moment when the height is 9 centimeters. Okay, so we're going to set up the situation. So pi thirds r squared times h. But remember, we don't want to have two variables there, which is usually why you need two formulas. But this time, we're just going to substitute h over 3 in for that r right there. So that's what I did here. And now we're going to square this. Well, h squared is just h squared. 3 squared is 9. And then 9 times 3 is 27. So hopefully I simplified that. Yep. So this is what we have. We have h squared over 9, pi thirds times h squared over 9. You multiply that, you have pi over 27 h cubed. And now you're going to take the derivative of that. So the 3 will come down in front, and then that will be h squared. So it will be 3/27 pi h squared dh dt, because remember it's related rates, so we use implicit differentiation. And then 3 over 27 cancels to 1/9. So hopefully that was that next step. Whoops. So we have our h squared and our dh dt. We have our 3 pi over 27. Then that cancels, leaving pi over 9, h squared dh dt. And right there is where I went ahead and substituted for h. What do we say h was? 9 centimeters. So h squared, 9 centimeters squared. dh dt is 4 centimeters per second. Now we're going to have to square that, so that becomes pi ninths times 81 centimeters squared times 4 centimeters per second. Well, 81 divide 9 leaves 9. 9 times 4 is 36. So that should leave 36 pi centimeters cubed, because this centimeter squared per second. Hopefully, I didn't make a clerical error. There we go. 36 pi centimeters cubed per second is how fast that volume is changing at the exact moment the height is 9 centimeters. All right, that's it for related rates of a cone.